Electrical machines, particularly rotating electrical machines, are basically electromechanical energy conversion devices. That is, if you have a electrical machine, it can take electrical energy as input and give out mechanical energy as output, or we can reverse the direction of energy flow, that is mechanical energy can be input and electrical energy can be output. When an electrical machine accepts electrical energy and gives out mechanical energy, we say it is a motor. When it accepts mechanical energy and gives out electrical energy, it is called a generator. However, it is the same machine, the same physical object which we call the electrical machine performs both these operations. Therefore, every electrical machine can be either a motor or a generator depending on which is the input and which is the output. Now, invariably almost all electrical machines are of rotating type. I said almost because some are not. The reason is very simple, one of compactness. In order to either accept or give out mechanical energy, there has to be some motion of some physical object of the machine against an opposing torque. Now, if you want to get continuous mechanical energy output, the motion also has to be continuous, and it is convenient to have a rotating motion which can be continuous, but still be kept within a finite volume. That is why almost all electrical machines are rotating type. Now, let us see how we can induce a rotation in an electrical machine. The principle is by the principle of magnetic attraction or repulsion. Let us say this is the inside of a electrical machine. Somehow at the center of it I have kept a magnet with this north pole and this as the south pole. This is not attached to the other part of the machine and it is free to rotate. Therefore, this body is called the rotor and this body which remains stationary is called the stator. Every electrical machine will have these two components. However, their placement may not exactly be like this. There are some construction where the rotor is outside while the stator is inside. These are called inside out construction. However, normally in more often than not the case will be where the rotor will be inside the stator. Now, let us see how we can make this rotor rotate. Here I would like to mention that we are taking a cross sectional view of a electrical machine. Actually, it is a cylinder kind of a construction and this rotor also run the whole length of the machine body and normally hinged, supported by two bearings at the two ends. Let us see how we can make this run. Suppose I somehow create another north pole on the stator on this side and a south pole on this side. Joined. Of course, there will be a force that will be repulsive force on this north pole, there will be a repulsive force on this south pole, there will be attractive force in this direction and there will be another attractive force in this direction. As a result, this rotor will try to align itself with this north pole and this south pole, and in the aligned position it will look like this. In fact, the rotor will not stop here, because it was moving, it will somewhat overshoot this position. However, if the stator north and south poles remains, this pole maintains this polarity, it will be brought back, because there will be opposing restraining force, it will be brought back in this position. However, now let us consider a different situation. Just when it is aligning, let us say I change the position of the stator poles. Now, I make this south, this north, this is south, this was north. What will happen? Now, there will be a repulsive force which will force this rotor in this direction, and there will be another repulsive force which will force this rotor in this direction. So, this magnet will continue to rotate. Now, there is one basic problem to this approach. First of all, how do we shift this polarity of these two magnets? This can be done without involving physical magnets. If these are electromagnets, we can change this by changing the direction of the current, and that is exactly what is done in an electrical machine. There is another problem, is that how do we get a magnet on the rotor? There are two ways of doing it. One is we can use a permanent magnet, or we can use another electromagnet in the rotor. In fact, the arrangement can be reversed. That is, the permanent magnet or the electromagnet can be on, permanent magnet may be on the stator and the electromagnet may be on the rotor. This is what is done in case of a DC machine, at which we will have a slightly more detailed look. So, let us see the construction of the cross section of a DC machine. As I mentioned earlier, there are two fixed poles. For simplicity, we are assuming only two, can be more. Which are either permanent magnet or electromagnet. Let us say this is north pole and this is south pole. Inside we have a cylinder carrying a electromagnet. Let us say for simplicity made up of only one coil. Now, if the current polarity is in this direction, that is current is entering through this and coming out through this terminal, then it will produce a north pole in this, it will produce flux lines in this direction, that is this will be an equivalent north pole, this will be an equivalent south pole. So, when this happens, then there will be a repulsive force acting on this rotor body in this direction, and there will be a repulsive force in this direction, due to which this rotor will try to rotate, and at one position it will come to the aligned position. This is north pole, this is south pole. The aligned position, it will become somewhat like this. This is the north pole, this is the south pole by the rotor electromagnet. Of course, it will not stop here, as before, due to mechanical inertia this will try to overshoot this south pole. Now, this is where we need to change things. If we want to continue, if you want to make this rotational continuous, we will need to change either the polarity of this or the polarity of this. In a DC machine, it is the polarity of the rotating conductor that is changed. That is, we make now this at this point we make this a dot and this a cross, so that the repulsive and the attractive forces continue in the same direction. The device by which this change of polarity is effected is called a commutator. So, let us see how a commutator will be placed. So, these are the conductors. Commutator obviously must be in the same body as in the rotor, because it will make permanent contact with the conductors. So, let us say this is one commutator segment, this is another commutator segment, this conductor connects to this one connects to this. So, this commutator is basically a kind of a ring, conducting ring, split into two parts in this case and connected to the two sides of the coil. However, now how do I make external connection? How do I make external connection to this commutator? That is done through what is called brushes, which can slide on this commutator ring. Where should be the position of the brush? The position of the brush should be such that in the aligned position it changes the polarity of the current flowing through them, through the coil. Therefore, here for half the cycle they should connect to one commutator, for half the cycle should connect to this conductor, the same brush should connect to the next other commutator for the rest half. Therefore, we have to connect the brushes on this commutator, so that when it is in the aligned position it should change. If the brushes are here, which is supplied with a direct voltage, in this figure we have shown that the cross is connected to the positive terminal, the dot is connected to the negative terminal. In this instant then this commutator must be connecting to the negative terminal and this to the positive terminal. So, this will be the direction of rotation is this should be the negative brush and this will be the positive brush. So, when it further rotates, the cross conductor will get connected to the negative brush, whereas the dot conductor will get connected to the positive brush and the polarity of the current through this winding will change, which is necessary to maintain the rotational motion. So, this is the working principle of rotation in a direct current machine. Some of you may be familiar with this already. However, how does mechanical energy gets converted to electrical energy and vice versa by this method? For that, we will have to look at another phenomenon in this coil, which is the induction of voltage, which is governed by Faraday's law. For that, what we will do? We will draw what is called a developed diagram of this machine, which essentially means we cut this rotational structure and draw it in a unfolded manner or unrolled manner. So, this is the north pole on the stator, this is the south pole on the stator, and let us say this is the armature. In the unaligned position, let us say one conductor is below the north pole, another conductor is below the south pole. Now, the north and south pole on the stator are producing magnetic flux, and the flux density is maximum under the pole and minimum between them. To some approximation, we can approximate it by the flux density to be almost a sine wave. This is the plot of the magnitude of the flux density over the armature surface. It is easily understandable that in this unaligned position, the net flux passing through this coil is 0. However, this armature is moving. This armature is moving in this direction. So, after a while, the diagram will look like while the flux density waveform still maintains its previous pattern, that is 0 at these points, comparing these two diagrams, we can see that there is a change in total flux that passes through the coil, that is, there is a change in flux linkage. In this case, the unaligned position, total flux passing through the coil was 0. In this case, what has happened? The total flux passing through the coil has become positive, because it now more flux pass through this total positive net flux passes through this coil from the armature towards the pole. Now, so there is a change in flux linkage, and we can define a rate of change of flux linkage with time, and according to Faraday's law, in which case there will be a voltage induced in this coil. What will be the polarity of the induced voltage? The polarity of the induced voltage will be such that it will try to oppose the flow of current in this conductor, because that is the cause. Because of this current flow there is a torque generated, and that is why the body is moving. It will try to oppose the flow of current in this coil. Therefore, what will be the polarity of the induced voltage? Polarity of the induced voltage will be this negative, this positive. So, if we look at the coil, if we look at the armature coil, there will be a induced voltage in the armature which will try to oppose the supply voltage which is forcing the current. Therefore, in order to send some current into the conductor, some amount of electrical energy has to be spent, which is given by electrical power is given by E into IA. So, this is the electrical energy accepted, and hence because of that there will be a torque generated in this machine which will make this body rotate. Now, if we have some load torque which may try to slow it down, and hence some mechanical work will be done. In the process, the electrical energy supplied by the source will be converted into mechanical energy, and this is called the motoring mode of operation. What will happen if I want to make it operate as a generator? In the generating mode of operation, the reverse will happen. In the generating mode of operation, a prime mover will be used to rotate this machine. So, voltage will still be induced because there will be a rate of change of flux linkage. Now, as long as we are not connecting any resistance or any external circuit to the coil, there will be no current flowing, hence there will be no repulsive force, as I have indicated here, repulsive or attractive force, and there will be no mechanical work done. However, as soon as I connect an external load which may be a resistance, then a current will start flowing. The current will flow in such a direction that it will try to slow down or stop the motor. That is, it will produce a torque. The current direction will be such that it will produce a torque which will oppose the motion, and hence in order to rotate the rotor against that torque, some amount of mechanical energy has to be spent. This mechanical energy will then be converted into electrical energy in the form of current flowing in an external resistance, and thus mechanical energy will now be converted into electrical energy, and the electrical machine will operate as a generator. So, this is the principle of electromechanical energy conversion in a electrical machine. So, we see that the same construction, the same physical device can either work as a motor or as a generator depending on which is the input. If electrical energy is the input, then it will produce mechanical energy and will be called a motor. If the mechanical energy is input in the form of a prime mover, then it will produce electrical energy and it will be called a generator. So, this is the basic operating principle, but a practical DC machine will be somewhat more complicated than the idealized picture that I have shown. Let us look at those practical issues. The stator I said carries 2 pole. However, the number of pole need not be restricted to 2. You may have more number of poles. So, the pole arrangement will be north, south, north, south. This is the one modification in the stator that a practical machine can have. The number of poles of course will be even, because there has to be a pair of north and south pole, but it need not be 2. Similarly, looking at the armature, it will never have only one conductor. In fact, that will be a very poor utilization of the armature surface. Not only that, we have seen if I have only one conductor, then the force of attraction or repulsion will be maximum in this position, but as the armature rotates and comes near the aligned position, the forces will reduce. So, the torque produced by this primitive machine will not be constant, but it will be highly time varying, which is not desirable. In order to avoid that, the armature is equipped with what is called a distributed winding. So, you will have several such coils . However, the direction of current flow in half of them will be cross and half of them will be dot naturally, because one is the return end of the other. But it is important that in order to, now we can understand the extend the principle of operation for this practical case. Let us say at any instant this is the polarity of current. Obviously, this arrangement will still produce a north pole in this direction and a south pole in this direction. Hence, there will be a force of repulsion on this body, and hence a torque will be generated. So, the armature body with all its conductor will rotate. However, it is important that as it rotates, the overall picture of the current conduction must not change. That is, the top half should still be carrying all cross current, the bottom half in this diagram should still be carrying dot current, although the current in individual conductors may change. That is, a commutation arrangement has to be devised so that as and when one coil passes the commutator, its direction of current changes. This is necessary in order to maintain a uniform unidirectional torque in this machine. So, let us say how a commutator is to be arranged for this particular machine. For simplicity, we will assume, let us say this is one coil. All these coils in a DC machine are what we call series connected. So, this is another coil, this is another coil, and this arrangement continues till the last coil closes on this first coil. So, this is called a closed winding. How we will change the direction of current in these coils? For that, we will have a commutator arrangement. Commutator, as I have mentioned earlier, is a annular structure. Previously, with only one coil, we had two segments, but with multiple coil, now I should have as many segments as there are coils. And each coil will be connected to one of these commutator segments, and these commutators must be insulated from each other using some insulating material. How the commutation process takes place? Commutation process takes place when this one of these commutator segment is connected to the positive bus or positive brush, and another is connected to the negative brush. So, at any instant, let us say current is flowing in this direction. On reaching this point, the current has two paths to flow, one it will go this way, another it will go this way. So, the current through this coil is flowing at this point in this direction through all of them. And this direction. Now, let us say this machine is moving in this direction. So, what will happen? After some time, the commutator segment will move to this position. This will be the new position of the commutator. Please note that once the commutator comes in this position, then the coil whose two ends are connected to these two ends of the commutator are shorted. Therefore, this coil, this particular coil in this case, gets shorted. How the current will flow then? Since this is shorted, there will be no current. However, the current will still flow in this direction through this coil, previous as before, and through this part of the coil as before. Next, the next instant, previously the commutator was on this segment, next it has shorted these two as it is rotating, and finally it will arrive in this. Now, what will be the direction of the current? Current is still coming like this, it is flowing like this. In this coil, this was the previous position of the commutator, and in this coil it will now flow like this. Comparing the direction of these two coils, we see that the direction of the current that was shorted, which is said to have undergone commutation, the direction of that current in that coil has changed. Therefore, the coil in this picture that undergoes commutation, before commutation it had a dot current and the corresponding other side has a cross current and the corresponding side has a dot current. Then when it undergoes commutation, this becomes a dot and this becomes a cross, so that the net, all the conductors on the top side remains of cross polarity, while all the conductor on the bottom side maintains dot polarity, and hence the overall picture and the position of the distribution of the magnetic flux produced by the armature winding does not change. So, although the armature is physically rotating, the flux produced by the armature winding maintains a same position as before, and this process the machine produces a constant unidirectional torque. One point is to be observed that in the process of commutation, that coil that undergoes commutation is shorted for a while, and we know that when these coils rotate under the influence of a magnetic flux, voltage is induced in them. So, if there is any voltage induced in this coil and it is short circuited during the process of commutation, there will be a very large current flowing in the coil and it can damage the coil. Therefore, it is not possible to short this coil when there is a induced voltage. So, only those coil in which the induced voltage is 0 will undergo commutation. This is ensured by placing the brush accordingly. The brush will connect to that conductor or that coil in which the induced voltage is going to be 0. Now, in this diagram, it will also be shown later that in order for the induced voltage in a coil to be 0, the flux linkage of that coil should be maximum. That is, the coil axis should be either coinciding with the axis of the north pole of the stator or with the south pole of the stator. That is, the coil sides should be at what we call the interpolar region. This is called the interpolar region, which is the middle position between two flux. That is, the coil sides should be on interpolar region and the brush must connect to those coils which are at the interpolar region. That is why it is sometimes said that the brushes in a DC machine are placed in at the interpolar position. Although physically, as we will see, the brushes may not be exactly in the interpolar position, but they will connect to a coil whose coil sides are at interpolar position physically, whatever that might mean. Obviously, if we have more than 2 poles on the armature, if we have more than 2 poles on the stator, the armature should also produce equal number of poles. That is, for this case we had 2 poles on the stator, armature produced 2 poles. Here armature should also produce four poles.
In order to produce poles in this fashion, the armature coil current polarities should be alternating. That is, if these are cross from one pole, these should be dots, then again cross, then again dot.
So, the armature must also be wound for the same number of poles as the number of poles on the stator, otherwise a steady torque will not be generated. So, the armature coils then will have same number of, will produce same number of poles as the stator. Now, these pole pairs north south, one set of pole pair will be connected in series. So, there will be several such pole pairs depending on the number of pole pairs on the stator. These pole pairs can be connected either in parallel or in series. Accordingly, there will be two types of armature winding called the lap winding and the wave winding. While the lap winding is series connection, parallel connection of armature poles, and the wave winding is the series connection of armature poles. We have not discussed about the possibility of connection of the stator poles. These stator poles are also usually not permanent magnet, but electromagnets that gives the ability to control the strength of these magnets. Now, there is a large variety of ways in which these field coils can be connected. There is a large variety of ways in which this field coil can be connected. They can be connected in series with the armature, giving rise to what is called a series machine. They can be connected to a separate source, by which we can get what is called a separately excited DC machine. They can be connected parallel to the armature, by which we get a shunt DC machine. Each field coil can have even two parts. One part may be connected parallel to the armature and other part can be connected in series with the armature. This is called the compound field DC machine. So, depending on the connection of the pole, we can have a large variety of DC machines. However, their basic operating principle remains as described. In the coming lectures, we will see a few constructional details and the characteristics of these different types of DC machines. Thank you.